And we're off. Okay. Today we are going to have new and exciting ways to look at conics. You looked at conics all these sort of old and boring ways. I didn't think they were boring. But it turns out there's many, many different ways to look at them. First I'm going to review something. And today is February 6, 2012. In this, the last year of our existence according to the Mayan calendar.
In the year of our Lord.
Yes, as they would say in medieval Europe. Okay, first thing. Some of this I won't get to today, some of it I will, but I gave you this 2 weeks ago. Take another look at it. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. General form of any conic. We're going to go through some information about this, some of which you should remember. It's the only ones you remember. What happens if A equals C? What do we have?
It's a circle.
Noah says it's a circle. Does everyone agree?
Yeah, it's a circle.
All right. What happens if A and C are the same sign?
That's an ellipse.
It's an ellipse. Very good. What happens if A and C are different signs?
It's a hyperbola.
Very good. Then we have.
What do you mean by
what
same
does
sign?
B do?
Like
positive
positive.
or negative. Like it'd be so A and C for an ellipse, so that's supposed to be
I'll
positive.
mention that in a
or
sec.
negative.
If A equals C, we have a circle. A and C are the same sign, we have ellipse. A and C are different signs, we have a hyperbola. If A or B equals 0, then what do we have? I'm sorry, I've been using these, not B, C. Joe, you got me thinking about C.
Is it a parabola?
Yes, then it's a parabola. And then if A and C are 0, which we didn't cover before, you would actually have a line. Because if all you have is x and y and a number, you're going to be able to rearrange it into slope-intercept form, or it'll be in standard form actually if A, B, and C. And all of these, did I leave anything else? Nope, okay. All of these are true if B is equal to 0. All of these are true if B is equal to 0, if you don't see that term. Because we never gave you any examples with the B term before. If B is not equal to 0, then the conic is rotated, and we start that tomorrow. Rotated conics we start tomorrow. They are a lot of algebra.
Is that,
Mixed
do we
with
have to
trig.
use the skills that we just used and then go a step
yes.
further?
Yes, we will. Several steps further. Actually, what you have to do is a lot of steps to get to that point. Basically, what we're going to do tomorrow is start using trigonometry to get from here to one of the forms you saw last week. And that form will be rotated. But these are your basic ways of identifying, and then we went over how, once you know what you're looking at, how to complete the square and figure out what it is. I think in the homework tonight I'm just going to give you identifying ones. But this starts tomorrow, and this is so you know what you're looking at. This is not the only way to look at conics, though. There are two others we're going to cover. One today, one a little later, maybe. Today, well, first off, who remembers what a parameter is, by my silly definition?
It's like a limit, like you can't go past it.
It's like an asymptote.
Yeah.
It's like
Pardon? It's what is it? It's like a what?
It's like a variable that you can't see.
Like a variable you can't see. Yeah, that's pretty much how I defined it. That'll work. What were you going to say about parameters? The same thing.
I was gonna say it was like a set of boundaries, like.
Okay. That's more like the English word, and you can use it this way for that. But remember my quick definition, if someone wants to follow me over to this board. All right, thank you. Then what we have is the short definition that will work for most high school math is dimensions are visible and parameters
Invisible.
aren't. They're invisible, however you want to write that. So that way to keep straight when you're dealing with parametric equations should be able to help you for a while. Now, parametrics. So this was the case where we had an x and we had a y, and they were both expressed in terms of t. T was most often time, can also be temperature, can also be an angle, can be all sorts of things, but we'll stick with t. Do you remember those? Parametric equations were x equals one function of t and y equals some other function of t. Now, what we're going to do today is take the parametric equations and ask you to remember a tiny, tiny bit of your favorite chapter on trigonometric identities.
Oh.
Remember those?
Wait.
Yeah.
Those were good times.
Pretty good.
It's
What was
like
the test that we all did value?
sine 2 theta, like plus cos 2 theta
Cosine,
equals
cosine,
y.
sine,
Oh.
sine.
Those things. Not too much. We're not going to go too much depth into them. Maybe. Depends. But here's an example. What do you think this graphs?
I
And
think
this
the
may also
lines-
look familiar.
I think the lines would have some kind of relation, whether it be parallel or
There's,
Remember, these
perpendicular.
are close. Hang on, before we go with that, remember these are
That graph's a period.
this is going to be parametric, so you're not going to see t.
yeah.
You're going to see the x and y depending on what t is doing. In fact, before I ask that open-ended question, let's make a little table here. Now, if we're dealing with sines and cosines, what sort of value should we plug into our table?
0.
Like pi over 2.
Very
Do
good.
you want radians or?
Let's do radians. Good review. 0, pi over 2. Where should we go from there?
Pi, pi, 3 pi over 4.
3 pi over 2, right?
Oh yeah.
So that would be 2 pi over 2,
yeah.
1 pi over 2, 0 pi over 2.
2 pi.
Okay. X is cosine. What's the cosine of 0?
Is 1.
What's the sine of 0?
0.
Okay, so that'll be the point 1 comma 0. What's the cosine of pi over 2?
Is 0.
And then what's the, I'm starting to write the answer.
1.
Sine of pi over 2 is 1. Cosine of pi?
Is -1.
Sine of pi?
0.
Very good. Cosine of 3 pi over 2?
0.
Very good. So remember on a graph, on a parametric graph, you can't see t. You can only see x and y. So the points are, which I'm about to label backwards, the points are 1, 0, 0, 1,
Oh wait, it just makes the unit circle.
makes the unit circle. Very good. And 0, -1. Now remember, it's a parametric equation, so it actually has a starting point. And I wasn't picky about this on the test, but you should indicate a direction. So mine's more of a potato, but if I could draw one, this would be the original unit circle going counterclockwise starting from 0 degrees. But we didn't prove that it actually is the unit circle, that these points will actually be circular in between, though it sure looks like it. I'll go ahead and tell you that it is. Here is one way to prove it. Tell me something about cosine squared of t plus sine squared of t. What does that always,
1.
always equal? 1. Doesn't matter what the angle is, doesn't matter anything else, it's always 1. Doesn't even matter if you're not on a unit circle because you'll be creating proportional triangles. The ratio will always take it down to 1.
Therefore x squared plus y squared equals 1.
There's
So then it equals a circle that
The radius of 1.
Boom, yep. This is the equation of a circle centered at the origin with a radius of 1. Perfect. You guys said it perfectly. So if x is cosine theta and y is sine theta, then by this identity, I know this is the rectangular relationship between x and y. If I started with this parametric relationship between x and y.
X squared plus y squared is the rectangular relationship.
Yep. That's the rectangular form of this parametric equation. You can see it by graphing points. You can only prove it by this identity.
Wait, so this is just be like building up all over time?
Yeah. There's a I had a goal to this class that everything you learned would actually come together and build on each other.
So you just winged that idea, right?
Yes, I don't plan this year at all. I just come in and make stuff up every day, and if it comes together, woohoo, or lines up with what we do in physics. So any questions on this one? Thing to remember, especially if you're graphing it, don't look ahead to where I was planning the lesson on the other board, Michelle. Thing to remember though, the parametric, unlike this rectangular equation, which just goes round and round forever, and we don't really think about where it stops or if it has a direction, the parametric form does have a direction. That's lost when you go to rectangular form, and if you're going from here back to there, you have to take that back into account. This is why the first time you guys went to parametric mode, remember when we first graphed in parametric mode on the calculator last fall, and everybody's calculator was 0 to 6.28 on the T min and T max? This is the most common use for parametric equations, so that's 0 to 2 pi. So that's why it starts that way. Okay, follow me back to this board, and I'll show you a couple other things you can do with this. So there's your circle. Another example. X equals, what am I going to do? Yeah, this one. 5 cosine t. Y equals 4 sine t. Just got to guess what this will graph.
It will
It'll
graph.
graph two circles.
You can't really get two things out of one set of parametric equation. Get an ellipse. You will get an ellipse for this. We could graph the points, but you know me, I'm a big fan of deductive over inductive, so I'd rather prove it. So let's see. From this, can I say that cosine t equals x over 5?
Yeah, because then it could be just 5 cos t.
Yep.
But can't you also do it like 5x squared now?
Oh, hold that thought. Hold that thought. You're on the right track, but I think you're about to have a reciprocal issue. Can I say sine t equals y over 4?
Yeah.
You could also switch it so that the t's are only on one side.
Well, then I'd have inverse sines and inverse cosines. And that's that's a good memory. You're remembering well, because that's how I told you guys to get rid of the t, was solve for it. If there's trig involved, that's the exception. If there's trig involved, that's too much of a pain.
So there's
This goes back to trig identities, but luckily there's only a few of them you have to remember. But for this one again, if I go to cosine squared t plus sine squared t equals 1, go back to this identity.
So we know it's going to be an ellipse.
No, it's going to be an ellipse. It's going to be x over 5 squared plus y over 4 squared equals 1. Which is going to become, since you can square top and bottom of a fraction, x squared over 25 plus y squared over 16 equals 1, which we know from last week is an ellipse centered at the origin with a semi-major axis of 5, a semi-minor axis of 4.
3 away from...
Boom. And c equals 3. Somebody saw the Easter egg.
Because of 3, 4, 5.
Yep. And the focus is 3 units away from the origin. In this case, left and right, because the larger number is under the x squared.
Wait, what goes into the? Wait, 3 goes into 6. Wait.
Because, like, you have to do the c
A
squared
squared.
equals the square root of a squared minus b squared.
Yeah, no, I know, but.
So the Pythagorean triples get rearranged.
Oh, so it's 25 minus 16.
Mhm.
equals 9, square root of 9.
Oh, okay.
So that's where Michelle was jumping ahead to. So you can still spot Pythagorean triples, except this minus sign means you have to have the larger 2 under here for the ellipse. And for the hyperbola, they work more like looking for Pythagorean triples on a triangle. Any questions on this one?
So what were we solving for exactly? We're solving for C?
No, in this case we're not solving for anything. I'm just
Okay.
showing you how these things relate. And the homework tonight might be, start here, tell me it leads to this. Start
Okay.
here, figure this
How
out.
would
they
they
have to
word
graph
tell you it leads to that? They would say put
Find
it in.
the parametric form of this
Do
rectangular
it the graph.
Okay.
equation. I don't think there's any graphing tonight.
Mr.
If there's, I'll probably take it out.
Can we do one that's backwards now?
Let me do one more of these
Okay.
first. There's one
So
more thing I wanna
that's
show.
rectangular. Those the 2 you gave us are rectangular.
No, the end result is the rect.
No, this is parametric.
Oh, okay.
Let me just be clear about that. Yeah, this is parametric. And I'm going to do one more of those. And then the end result is rectangular form. You'll be shocked to hear there's also polar forms of conics.
Woo.
Now the whole class is really following.
That's right, yeah. All right, go ahead and follow me back over here, though, with the camera at least. And let's see now. What if I have x equals, I'm trying to think of one of these.
200.
9 sine t and y equals 41 cosine t. Pretty sure I'm remembering that right. Oh, and then plus 3 minus 2.
Oh.
I already know what C is.
So then it's just gonna be x minus 3 squared all over 3 squared.
Well, you're jumping to
Over
the
9 squared.
All right, whoa.
No.
Slow down, Cowgirl. No, you're good. This is good. Okay.
X over
So you're gonna get
9.
x minus 3 squared
All
over
over 9.
9, yeah.
Wait,
Plus.
over 9 or over 9 squared?
Plus.
No, it's
No,
over
it's over.
9.
Pattern over here was it became over 9 squared.
Right. It is.
Yeah.
And then this is gonna be y
Y
plus
plus
2
2
squared all over 41 squared. And then to get C.
C is 40.
Just equal 1.
C is 40.
Who remembers that triple? Nice! And C, the distance from the center to the focus is 40, the 9, 40, 41 triple that I gave you guys on a test a while back, and most of you had to figure out by hand.
So the x minus 3 is coming, that's coming from the 9?
Here's where I want to speak for Michelle. If you solve this for sine, you'll get the sine of t equals x minus 3 over 9.
Okay.
The cosine of t then will be y plus 2 over 41.
Is it 9 squared?
Not yet. I'm just solving for sine and solving for cosine.
I mean down there.
Yes, that's 9 squared. So then, now I do sine squared t plus cosine squared t equals 1. So I have to square each of these solutions for sine and cosine of t. So instead of solving for t like we did to get rid of the parameter last time, you just solve for the sine and cosine of t and then use this identity. There's one more identity that comes up on these. As long as we're sticking to conics, you should only really need 2. What else was different about this one?
It has like shifts now.
Has the translations, yeah, the horizontal and vertical shifts. Quick note, notice that this is an intuitive shift when the 3 is over here. This is a counterintuitive shift when it's inside the function, and we're in rectangular notation. So you move 3 units to the right. Well, up here it's x and it's plus 3. There's your 3 units to the right. Here it's y and minus 2.
Wait, when you move 3 units to the right and left? Because it's an ellipse, so you have to go on.
Yeah, from the center, yes. Well, I'm thinking where the center would move.
Oh,
No,
okay.
you move 9 units right and left and 41 units
Oh, yeah.
up and down.
Oh,
Okay, yeah, your
Yeah,
company says Yeah, the center just moves 3 units right, counterintuitive here, 2 units down, but the shifts are intuitive here. And actually, if you know for a fact you're looking at ellipse, which system do you think actually makes it easier to look at and graph quickly?
The bottom one, the rectangular.
Rectangular.
Really? That's just, I mean, that's just because you're used to it. I don't, see, if I look at this,
Because
I'm
you
like,
have the y and the x.
Well, I guess because you know that you have to
Oh,
go 3
why?
units and then 2 units. Like
Wouldn't
that's
it
really
that
like
be? Because
total
that's
for
kind
you.
of like in y equals mx plus b form.
it's, yeah, see, I look at this and I'm like, the center's at 3, -2.
Oh, actually, that is a lot easier.
The major axis is 41, the minor axis is 9, I'm done. I feel like the information's right there even more clearly, especially if I squared these. I know it's not a major
I
deal.
guess that's what we're used to.
Yeah, it depends what you're used to. I was just curious, and there's nothing wrong with preferring this. But I just like how you can see it there and move it around more easily. Anyone notice one other thing I switched?
Nothing you just-
It's a little bit subtle.
Wait, from that to that? What do you
From
mean?
what I've done for the other 2 examples, one of which I've
You
erased.
put,
What is
Wait,
it,
what are you
H
gonna
and the
say?
K?
There's
What did I say X always
the
relates to?
the cosine, and you switch the cos and the sine.
I have the X with the sine and the Y with the cosine now. You're
allowed
allo-
to make a difference.
You're allowed to do that. It won't make a difference in the shape. Remember I said when you go from polar to rectangular, you lose direction
Okay, so
and starting an
that's
input?
probably
So this
cosine
is
always
polar.
probably means that it's a major axis, and sine means probably that it's
No, that's totally by this length.
Oh.
So by this length. But what this will do, I'm not going to go into detail on this now, and I'll let you fiddle with it if it comes up on the homework tonight, but I've changed, if you made a table, I've changed the starting point and the direction. This will definitely go clockwise, not counterclockwise.
Wait, but we don't have
Why
to
is
graph
that?
this for homework.
No. I'd have to show you with a table. Wasn't actually what I planned on teaching today,
Okay,
but
then don't. That's fine.
some of this isn't like the way the universe is meant to work. Remember I said math falls into a couple different categories. What seems to just be true because a supreme being or the universe or nature or nothing at all just made it that way, whatever you believe in, and other things that we definitely made up. Everything about the unit circle and cosine always lining up with x and sine always lining up with y, that is all intentional. That's all arbitrary. They could have easily named things differently, phrased things differently. But what happens is if you switch the sine and cosine, you tend to get a clock. You tend to get something that's, as long as there's no positives or negatives or other things mixed in, you'll get something that starts at the top of the y-axis
because
and
X
go
is
clockwise.
the sine and Y is the cosine.
And
you're
you're
saying?
switching y and cosine, so you're inverting it. It's like making an inverse function, if you remember those from last
So
year.
if you switch them, then that's why it goes.
So instead of starting on x and going counterclockwise, it'll start on y and go clockwise if you switch them. But having it, as you guys who are, especially the 4 of you who are in physics know, trajectory works a lot better if you imagine starting horizontally and going up at an angle from the horizontal. And I think that's why Descartes and others chose to have cosine always line up with x and y always line up with sine. Just so trajectory will work more intuitively to them and hopefully to us. But yes, you can take care of the shifts. And Michelle, it was very impressive looking at this and jumping to here, by the way. That was quick. Okay, so coming back over here for another example. And I'm going to go ahead and give you this identity in advance, which you should remember, but remember 1 plus tangent squared theta equals secant squared theta? Okay? Just a little bit of algebra, I can rearrange this to secant squared theta minus tangent squared theta equals 1. That's why I'd like to let you guys stop at this step a couple of times. So what do you think happens if I say x equals 5 secant squared theta and y equals 12 tangent squared theta? Not tangent squared. Hello.
That's why I was so confused. Because you could-
Rewind. Go back. Yes.
Because
5.
wouldn't that have just been like 5 plus whatever?
No, that would be, yeah, that would have been really silly. That would have been a line, I guess. X minus y equals. Anyway, That's a great trick question for the next test. I just accidentally thought of. Of course, our audience at home didn't get to see it at all, so can you make sure that's lined up with the board, Jen?
Yeah, sorry.
Thanks,
sorry.
it's clear. I
Sorry,
didn't say
guys.
anything. That's fantastic. At least my typo was only talked about.
Big D's.
Okay. What's this going to be? What's it going to look like? What's it going to graph?
Well, you know that it's going to be a ellipse. No.
No, it's going to be a hyperbola because the y term would be negative.
Bingo. The y term would be negative. Yes, it's going to be a hyperbola.
Wait, but is it?
Okay.
How do you know that?
Well, let's go through the steps and see if that helps you. Secant t will be x divided by 5, right? Double check me on this after the mistake I just made.
Would it just be 5 divided by x? So it's secant, so it's opposite.
Oh, no, that'd be cosine. That'd be if we were turning it back to cosine, it would be the reciprocal. Not the opposite, the reciprocal.
Okay.
But tangent t equals y over 12. And now don't even worry about changing it into sine or cosine. Just go straight to this identity. Plug in x over 5 for the secant, y over 12 for the tangent, and I'm going to get x over 5 squared minus
What about the 1?
y over 12 squared equals 1. The 1 is actually necessary.
But how do you know that it's minus?
This identity up here.
Oh, whoopsie. I'm gonna pretend I didn't just ask the question.
So now, so what are we, Joey said we're looking at a hyperbola. Was he correct?
Yeah.
Yeah.
Since I can't square anything on the first try.
So 5, 12, 13.
So what is C?
It's 13.
Yep, very good. So the foci of this hyperbola are 13 units from the origin, which makes sense because the origin is the center in this case. Which makes sense because it has to be outside, farther away than the vertices. The vertices are going to be at 0, 12, 0, 12, and 0, negative 12. No, they're not. I was kidding. So it's going to be, we're going to get to graphing this again later. But yes, it's 5, 12, 13 relationship, and you could graph this with the mad skills you learned last week, which I'm apparently brain farting on at the moment. I'm not going to try and say it without drawing it. So this identity is the one that lets you recognize a hyperbola. Don't try to get too creative with these. Don't try to solve for t. If you see a mix of secants and tangents or sines and cosines, you're either looking at a hyperbola if it's secants and tangents, an ellipse if it's sines and cosines.
Wait, can you write that down somewhere?
Wait, are we going to get parabolas or no?
Yeah, but they're not as difficult. So a parametric ellipse will be x equals a sine or cosine of t plus k. This is the exact same notation, exact same lettering I used for when we did it this way. I will say that again in a much better way. And y will be b sine or cosine t plus h. These parametric equations, let me write it this way. I'm going to write the cosine over the sine. What does it mean when I flip them?
Not there.
It's inverse.
If this is sine, then this has to be cosine. No, not in this case. There's no fraction bar. This is sine, or it's like plus or minus. So if it's sine here, it has to be cosine here. No, just different. Sorry. If it's cosine here, it has to be sine here. Okay, so this is or. And then this will switch to x minus k squared over a squared plus y minus h squared over b squared equals 1. So I've used a, b, k, and h consistently with what we did last week. That's for a parametric ellipse. The parametric hyperbola if someone will follow me over here. Thank you. The parametric hyperbola is going to be x equals either secant or tangent of t times a plus k, y equals b times either the tangent or secant of t, whichever one you didn't see up here, plus h, and this will change with a little manipulation to x minus k squared over a squared, where this could be plus or minus, and then this would be minus or plus y minus h squared over b squared equals 1. I haven't covered every possible variation on how the pluses and minuses can work here, and I won't have time to, so you may be required to be a little bit clever tonight. But this pattern will work. If you don't see alternating, if you don't see a sine and then a cosine, or you don't see a secant then a tangent, if you don't see differently, these could very well be something totally different. So it really has to be one of these patterns for it to be a conic. Parabolas. There's no trigonometric way to express a parabola parametrically. I mean, there probably is, but I don't know it. And it's not common. So parabolas are more like what we did before. For example, if you had something like, what are some of the examples we did last time? Like x squared equals 8y. This would be a parabola going up with p equal to 2, the focus 2 units away from the vertex. This is a case where you would, I would solve it for y. So y is 1/8 x squared, right? And then my parametric equations would be x equals t, y equals 1/8 t squared. Remember that we did this cheap little trick with parametric equations before?
No, I mean
We did it with lines. Just make x equal to t,
Oh yeah.
and then just plug it in for there.
Oh,
Yeah.
Yeah, that's all you do for these parabolas. The only difference is, what if you get one where the y is squared, since we introduced those last week? I'd make y equal to t then. So if I had y squared equals negative 32x, for example, I would just say y is equal to t, and then x would be negative 1/32 t squared. Then you avoid the problem of having to deal with plus or minus roots. But there's no fancy trigonometric identity trick to parametric parabolas. It's just the same way we did them before. You have to dig deep into your memories for that. Any questions on these? Homework tonight will be a little bit going back and forth, and so really just going to be it, going back and forth between parametric and rectangular. All right, then I'll give you the homework. Jen, go ahead and hit the button.